Let's look at OpenStax College Physics Volume 1, Chapter 2, Problem 59. By taking the slope of the curve in Figure 262, verify that the velocity of the jet car is 115 meters per second at t is 20 seconds. B. By taking the slope of the curve at any point in Figure 263, verify that the jet car's acceleration is 5 meters per second squared. And there's a note above that saying that there is always uncertainty in numbers taken from graphs. If your answers differ from expected values, examine them to see if they are within data extraction uncertainties estimated by you. So let's start looking at part A. We're using the first graph, so we're looking at this graph over here, and we want to verify that the jet car's velocity is 150 meters per second at t is 20 seconds. So let's look at the axes on our graph. On the y-axis, we have position. On the x-axis, we have time. And we're interested at time is 20 seconds. So 20 seconds is over here. So that means that we will have to draw tangent line of this graph at time is 20 seconds. And you can see that this is going to be a little bit complicated because we have to eyeball this. So I'm going to try to draw this tangent line, and I'm going to be playing around with it. So let's say that I'm going to stop that over here and drag this all the way there. And actually, it doesn't even touch the graph at 20 seconds where the x is 20 seconds. So I'm going to change this a little bit. Looks better, I think. So I'm going to pretend that that is my tangent line. It's not perfect, but it's as perfect as I can make it. Then I will have to find the x and y that correspond to this line. So this would be my x over here, and my y is going to be this. And to do that, I'm going to have to draw projections onto the x and y axes. So I'll try to do that over here. So I'm hoping that that's kind of vertical. And then I'm going to draw another one this way, and hoping that this is horizontal. I should probably extend it over here. Maybe that's a little bit too low, so maybe that's a little bit better. I don't know. So that's supposed to be a rectangle. So I guess I do have a rectangle tool. So let me try to use that and see if I can draw the rectangle from here. Let's see, bring this down. So I see that that line wasn't completely parallel. I'm going to do that over here. So I'm playing around with my software, really. It is not something that you would have to do, but I'm trying to be as careful as I can. So I'm looking for a velocity, and velocity means that I want the delta y divided by the delta t. I want the y-axis divided by the x-axis. So on the y-axis, I have almost 3,000 meters. So let's call that, let's see what the increments are. So this is between this line over here and that line over there, that's 500. So delta y, let's say, is about 2950 minus 0. It's a number that I'm really guesstimating. And on the x-axis, I want a delta t, but the delta t goes from this point to that point. So this point, let's see, that here would be about 7.5. So maybe that point, the intercept there is about 6.5. So that would be negative 6.5 seconds. And this, so if this here we're about 32.5. Maybe that is 33. So I have 33 minus 6.5. Let's plug that into my calculator. And I'm getting 111.3 meters per second. So all that playing around and trying to read the values on the x-axis and on the y-axis paid off because I have a very close speed to the actual speed. So again, the slope then of position versus time graph gave me the velocity, and by being as careful as possible, I was able to determine that that velocity was very close to what we were told the velocity was at time is 20 seconds. Now, in part B, we want to take the slope of this curve to find the acceleration. So this curve is velocity versus time. Velocity is on the y-axis, time is on the x-axis. And again, I will try to draw, I think I'll try to draw my rectangle from the very beginning to see if we can get this as good as possible. So let's move this a little bit here. Okay, and it seems like I have to change this a bit. There we go. So it looks to me like the acceleration, which is delta v over delta t. Again, since it's a slope, it's y divided by x. My y value over here, so this is 160, that's 180. Halfway between these two would be 170, but it's a little bit less than that. So how about we call that 168. So we have 168 minus, so I want this value over here, and that's less than 20. So maybe 17. So 168 minus 17 divided by, this value is 30 minus 0. So if I plug these numbers into my calculator, let's see what I'll get. And I am getting 5.03 meters per second squared. So again, playing around and trying to be as careful as possible gave me really good results. And this is not something that I was able to do beforehand because it really depended on how I drew my graphs here, how I drew this slope. So this was completely done without any prep work. I had to estimate these values just while talking at this video. So it pays again to be as careful as possible, draw your slopes as well as you can, use a ruler to make sure that you get completely straight lines. And in this case, there was no slope to be drawn because this is a straight line as it is, so the slope coincides with this green line that was given to us for velocity versus time.